Hello class, for this video I'm going to cover correlation and regression together. And so we're going to talk about associations and predictions, which is kind of the distinction between correlation and regression on some level. When we talk about associations, there's really three types that we're going to focus on. For example, if we think that intelligence is related to income, they're somehow connected, we could draw a double arrow where there's just an association, there's just a relationship between them. We're not saying that it goes in one direction or the other. We're not saying that one causes the other. We're just saying that they're somehow connected or associated with each other. A different way to represent that intelligence and income are connected with each other, associated with each other, would be to use a directional arrow. So here, the top one, we see intelligence predicts income. Intelligence causes income. So when we see a one-way arrow, that suggests that there's causality, there's a direction. One thing on the left-hand side of the arrow leads to the other thing on the right-hand side of the arrow. And we could look at this and say intelligence leads to income, or we could say that income leads to intelligence. And you can think about it as it is possible that if I am smarter, I do better in school, and thus I get a better job, better letters of recommendation, those types of things. I perform better maybe in a job interview. It is also possible, though, that if I come from a family that has a reasonable amount of money, they then provide me with certain opportunities, things like that. And because of that, I then am able to make a better income because I have their connections. I'm using their connections. And then because I have their connections, I go to better schools, and that leads to better intelligence. Now, in describing that, we introduce this idea of third variables, and we'll talk about those in a moment. But that would be the third type of association, where in fact intelligence and income might be related to each other, but the real cause of intelligence and income are family resources. Where if you are in a family that has books, we do in fact see that the more books in a house, the more literate individuals become, they tend to score better on SATs, they tend to do better because they had early language exposure. And we find that parental education is related to the number of books in the house. So, because of that, the family resources then lead to an increase in intelligence, but also we see that families that are more resourceful, families that have more resources, tend to, again, have connections. They tend to be able to get people jobs. And not get them the job, but get them an interview. And if you have a foot in the door already and your family member knows somebody that works there, the likelihood that you get a job there is then increased because the likelihood that you get a interview is increased. And so these are the three types of models. This first model, where we have intelligence and income and they're connected with that bidirectional arrow, so it could go either way, both ways, that's what we typically think of as a correlation. And then with a bivariate regression, there is some implied directionality in the regression itself because we typically have an outcome variable. We talk about that as y, and we have the predictor variable, which is talked about as x. Now, just because you run a regression doesn't mean you can prove causality because that depends on the nature of your data. Is it experimental? Did we manipulate something? Do we have temporal precedence? And we'll talk about those things later. But while a regression in and of itself can't prove causality, it on some level implies a certain causal relationship with one of the variables being the outcome, being the dependent variable. So when we talk about correlation, correlation is a statistical procedure that's used to describe the association between two variables. And when we say association, it gives us two pieces of information. It gives us the strength of that association and the direction of the association. And by direction, there we mean, is it positive or is it negative? As intelligence goes up, we would anticipate that income also goes up. That's a positive relationship. What we might also expect is that as intelligence goes up, unemployment goes down. And that would then be a negative relationship where the likelihood on the second variable is decreasing as the other variable increases. And we'll talk more about those in a moment. So here we can see that again, with a correlation, it doesn't really matter which variable is X or which variable is Y. We're just saying that they're associated with each other. So if we think that weekly income is associated with IQ, we could put weekly income as the X variable on the X axis, and we could put IQ then on the Y axis. Conversely, we could put IQ on the X axis, which is what you see on the right hand side, and income could be on the Y axis. These data are identical, they're the same. You can do what's called a scatter plot with both of them, but the X and Y axes are basically interchangeable in a correlation because there's no implied directionality. So if there is a directionality to the data, then we typically put the X variable as the predictor variable, the variable that comes first, the variable that causes the outcome, which we then put on the Y axis. So as I mentioned, these both provide an example of a scatter plot, which is visually how we show continuous data between two variables. I mentioned the x-axis. This should all be familiar to you from high school math, but if it's been a while, the x-axis is the one that is horizontal. The y-axis is the vertical axis. And within each scatter plot, we have multiple data points, and I've highlighted one here that potentially would be what's called a bivariate outlier. And we'll talk about bivariate normality in a moment, but basically a bivariate outlier is one that doesn't fit close to this fit line or this regression line as we refer to it. With regression, again, there is an implied directionality. So a regression is also a statistical procedure. And here we can determine an equation so that we can try to predict future outcomes with existing data. IQ and income are related. Let's say that it's the one on the right. Intelligence leads to income. I could then potentially in high school give you an intelligence test and approximate what type of money you would make later in life. And that then allows me through this regression equation that we would get from the regression to say, okay, this is your IQ. What do I think you will make? What's the likelihood that you make that? So with this, it does matter what is on the x-axis and what is on the y-axis. If income predicts intelligence, then we would show the scatter plot that's on the left. Conversely, if we think intelligence predicts income, it would be more appropriate to show the scatter plot that's on the right, where IQ is on the x-axis, IQ is our predictor, and weekly income is on the y-axis. That's our outcome variable, our dependent variable. Now, just to make it clear, especially in experimental research, when we talk about an independent variable, it's what's known as a true independent variable, meaning that we have manipulated it experimentally. In correlation and regression, a lot of the times we are working with naturally occurring variables. I didn't manipulate IQ. Because of that, I talk about it as an independent variable. I talk about it as a predictor. But if I didn't manipulate it, it is not a true independent variable. It is a naturally occurring variable, which again makes it hard to make a case that one causes the other unless I meet a certain number of criteria, and we'll talk about those criteria in a moment. From the correlation, we get a correlation coefficient. The correlation coefficient represents the strength and the direction of the linear association, and that part about linear is important. We'll talk about that later. It's because it's one of the assumptions of this test. But it represents the linear association between two variables. The correlation can range from +1 to -1, and if there's no relationship, then it should be close to 0, or more appropriately, if there's no linear relationship, it will be close to 0. So positive values indicate that as one variable increases, example, if intelligence goes up, the other variable also increases and income will go up. And conversely, it also is then true that if intelligence is lower, income will tend to be lower. So as one variable decreases, the other variable also decreases. A negative value indicates that there's an inverse relationship. So as one goes up, the other one goes down. And as the first one goes down, the other one would then tend to go up. So for example, class attendance or watching these videos. As video viewing goes up and you spend more time viewing it, more time taking notes, yes, I can see all that data in case you were wondering, then as that goes up, I would anticipate that the incorrect answers on an exam would tend to go down. So your score might go up. That would be a positive relationship, but the number of answers that you make that are wrong would tend to go down. That would be a negative relationship. So as time viewing the videos goes up, then number of incorrect responses should go down. That would be a negative correlation. And then a correlation of 0 means that there's no linear pattern between the two variables. So at the bottom here, on the left-hand side, we see a scatter plot with a positive correlation. So as we move up on the x-axis, we see that the y-axis scores also increase. On the second scatter plot, we see that as we move up on the x-axis, scores on the y-axis tend to decrease. So that one's going to be negative. And then we have two examples of a correlation that's probably close to 0. In the first case, we have this kind of cluster, this cloud, where there seemingly is no clear association between x and y. That would result in a 0 correlation. Also, this very last one on the right would also result in a 0 correlation, at least when we're doing linear regression, linear correlation, which is what we do in this class. However, as you can see, it's not that there's no relationship, it's that the relationship between them changes as you go up on X. So moderate change, moderate increase on X will improve performance, maybe, and we do, in fact, see these types of curves in some of our data. So if you've taken me in other classes where you have to do presentations, I'll often show this type of curve where a little bit of anxiety is actually good for you. It helps you focus, it helps you pay attention, it helps you be less likely to make a mistake. But if you have too much anxiety, too much arousal, too much stress, then we see decreases in memory, decreases in performance, decreases in response time. There's a number of things where we see this natural association. It's not linear, but it's also not really 0. But we would miss it if we did a linear correlation like we do in this class. So it's always important that you check a scatter plot visually to look for things like linearity. And we'll talk about that later because that's one of our assumptions in this test. There are two formulas for a correlation, and the correlation coefficient is represented by R, at least Pearson's correlation coefficient, which is the one we focus on, is represented by R. Both of them will give you the same answer. And in fact, I'm going to focus on the one on the left to show you why we get positive and negative values on correlations. Conceptually, I think it's very useful. However, the one on the right is more consistent with everything that we've done in Excel up to this point. So we're going to use the one on the right primarily in the practice and everything. So when we look at the one on the left, we see that we are working with z-scores. And reminder, z-scores have a mean of 0, they have a standard deviation of 1, they're a standardized distribution. We make them basically. So on IQ, if the mean is 100, which is the mean for the population, we would subtract the mean, we would divide by the standard deviation, and you can look back in your notes if you need a reminder or refresher about z-scores and what they are. But we would convert both the x and the y variables to z-scores before we even started. Now, conceptually, what this does is it makes it easy to see why R is positive and negative under certain conditions. So the mean of Z is always 0 because we make it to be so. Thus, anything to the right of the mean, anything above the mean would be positive. Anything below the mean ends up being negative when we're working with Z-scores. Similarly, we do the same thing on Y. We find the mean of the original scores, we subtract it, and then we divide by the standard deviation of the original scores so that we end up with a mean of 0, standard deviation of 1 in our z-scores on Y. And so when we look at it this way, we see that scores that are above the mean on Y also are positive, scores that are below the mean on Y are also negative. What this means for us, let's look at this data point here. So this individual's score is above the average on X and above average on Y. And we're creating a product term, so the z-score on X times the z-score on Y for that person for the correlation. So when I multiply a positive number by a positive number, I end up with a positive number. Similarly, we have this other person down in the bottom left, the quadrant. When I multiply a negative number by a negative number, so -3 times -3 would give me +9, for instance. So for this individual, because their z-score on X is negative, their z-score on Y is negative, we're going to end up with a positive product term, positive outcome. And so they're also going to be positive. So if you end up in either of these two quadrants, you're going to end up with a positive association. Well, not surprisingly, what that means is that if most of the scores are in those two quadrants, similar to what we see here. Now, there are some scores in these other two quadrants that are left unhighlighted, that are left white, but most of the scores are in these two quadrants where the product terms are going to be positive. Thus, the correlation will be positive because we're going to sum those all together. So if the majority of them are positive, then the sum of them will be ultimately positive. By contrast, when I multiply a positive number, so this score is positive on X, but it's negative on Y. When I multiply a positive number by a negative number, I end up with a negative score. If I multiply a positive by a negative in this other quadrant, so this one's negative on X, positive on Y, that's also going to result in a negative product term. And so if most of them are in these two quadrants, then we would end up with a negative association. And this data is not consistent with that, but if we look at the negative association that I showed you earlier, we see that most of the scores are in those two quadrants. Now, like I mentioned, ultimately, for the practice, for your homeworks, those types of things, I recommend this equation on the right-hand side. This equation on the right-hand side uses sum of squares similar to what we've done before. Now, it is a little bit different in the way that it does some calculations. We're going to talk about that, but it's going to be largely consistent with what we've done before. So because of that, from this point forward, I would focus on this equation on the right-hand side. But like I said, conceptually, I think the equation with the z-scores helps you to see why we end up with positive and negative correlation values depending on the quadrants that those scores primarily fall into. I've mentioned some assumptions. So for correlation and regression, they share three assumptions, and then regression has one additional assumption. The first assumption is homoscedasticity. Homoscedasticity is very similar to homogeneity of variance, except now instead of having a grouping variable where I'm looking at is the variability similar between my groups, the way we did it on the ANOVA and the independent samples t-test, I have a continuous variable. So it's still looking at is the variability on y, on my dependent variable, the same, but it's looking at is it the same for every score on X, and now X is a continuous score. So there's a lot of kind of groups basically. So if we're looking at the IQ, for instance, 100 would be a group, 101 would be a group, 102 would be a group, 103. Well, we really can't do that, and that's really not ultimately what we do, but it's similar to that conceptually, where we're looking at variability at each of those possible scores on X. The same way as before, if we were looking at men versus women, we wanted the variability in men and the variability in women to be relatively similar to each other. So when we see homoscedasticity, when we look at the scatter plot, it will look something like this, where there's variability on X and Y, but it's relatively similar, consistent across the range of X and Y. In contrast, heterogeneity or heteroscedasticity will look like we see here, where on the lower end of this scale, they're fairly tightly packed. There's very little variability, and there's considerably more variability as we see X or Y increase. And so because of that, there's more variability. The variability is not the same between these two different areas, regions. And so because of that, we would fail this test. Another assumption is linearity. And with linearity, we can see a relatively positive linear association here, where we could draw a nice, fairly straight line to represent the association between X and Y. By contrast, before, we saw that curvilinear relationship. And again, the problem is that for the first half of the data, the relationship is positive. For the second half, if we're moving towards the right on X, the relationship is negative, and thus a linear association, a linear correlation like we do, is actually going to say that there's basically no relationship, the relationship is close to zero. We look at it visually and we go, no, there's a relationship. It's just not a linear relationship. But once we violate that, we can't do a correlation or a regression, at least not the ones that we are learning in this class. We also have normality. And within normality, we have two types of normality. You've heard about univariate normality, where the x scores should be normally distributed, and we typically draw that nice curve. And now we have two variables, both of them are continuous. So x is normally distributed, y is normally distributed. And I have a note here, technically, we now are more concerned about the errors or the residuals, and we'll talk about what those are. But a lot of times we look at the histogram for x and the histogram for y to get a sense about that. Additionally, we now have added what's called bivariate normality. And bivariate normality means for each score on X, the Y score should be normally distributed. And for each score on Y, the X score should be normally distributed. So basically, if I go in and I take a slice, so on X, these scores, right, they're all the same. What do the Y scores look like within that data? I should see that most of them occur close to my predicted value, and I should see that some of them occur away from that. But I should basically see if I take a slice at this point that there's a normal curve of y scores at this point on x, and that should happen at every single point on x. The last assumption is causality, and this assumption is specific to regression because, again, regression implies causality. It can't prove it. That depends on our data. How well do we collect it? Do we meet certain criteria? But it implies it. And so the criteria for causality, one, the two variables must be associated. So we do need a correlation or an association between them, but we also need the cause to precede the effect. Well, it makes sense on some level that intelligence, IQ, probably comes earlier in life. We think that it develops throughout your life, but for the most part, it's developed through early childhood experiences. There's a little bit of a biological component, but then there's also a little bit of an environmental component, and those two interact. Well, that is all happening before you ever go out to get your job. Thus, it makes the most sense if there is a causal relationship between intelligence and income, it probably is that if you are more intelligent, you can make more money. But again, your parents' intelligence and your parents' income probably predates you ever entering the world. And so, because of that, it also is possible that your parents' intelligence and your parents' income influences both your intelligence and your income. And we'll talk about third variable problems here in a moment, but that introduces conceptually that issue. There also can't be a confounding variable or rival explanation. Parents' intelligence, parents' income could possibly explain the relationship between income and intelligence within yourself. And then there should be a reasonable theory that would predict or explain the causal effect. It does make sense that if you're more intelligent, you may get better letters of recommendation, you may be able to better navigate the job market, you might have more options, you might have been able to pick a career that more appeals to you, and so you're more motivated and excited about it. And so there is some reasonable theories, rationale that would explain why intelligence would lead to income. And so we would meet that criteria as well. As I mentioned, though, we do stumble into third variable correlations and then possibly third variable problems. And by third variable problems, what we mean is that we can't we can't prove a causal relationship between two things whenever there is some rival explanation. And so if there is a third variable, like parents' intelligence, parents' income, that possibly predicts both your intelligence and your income, then we can't say that your intelligence and your income predict each other or are correlated with each other indirect of parents. So that finishes up correlation. And moving on to regression, what we do in this class is called ordinary least squares regression. So visually, if we're looking at a scatter plot, we can explain ordinary least squares regression by starting with a regression line or a fit line. This is basically the line that best fits the data. And quantitatively, right, I visually looked at this and I drew the line on there. but we could quantitatively find this line using the ordinary least squares method. And by least squares, what we mean here is the squared deviation between this individual data point, and that would have to be for all data points, the same way that when we've done square deviations before, it was for all peoples. So how far does this individual deviate from their predicted score? So we use X to predict Y, and that line is a really good fit for some individuals, but it's not a great fit for everybody. Some of them are above it, some of them are below it, thus the need for squaring. And as we look at this, we would do that for all individuals. I'm not going to draw all of them on here, but I think this gives you enough to get the idea that we're having to do this for each individual. And then that allows us to produce this line where we predict y. So you'll notice that this has y prime. Sometimes you'll see it y with a little hat over it, like the upper part of a triangle. Both of those are used to say that it's the predicted value. What a value on y do we expect given x? So we know what x is for this individual. We know what x is for this data point. And then we have this predicted value on y, but that is different from the actual value on y. In fact, for this individual, their value on y is higher than that, and that is the residual. So we have y prime, which is where the line is for that score on x, and then we have the actual individual, and then the residual is basically the deviation of y around y prime. Now, we use the x score, and that's literally whatever the individual score is or some hypothetical score is on the variable. So if I know your IQ, and I've done this with 1,000 people before you, potentially I can tell you when you get out of here, and don't shoot me a bunch of emails. I don't have this equation in my back pocket. But I potentially, if there was a relationship between intelligence and income, I could approximate, hey, based on your intelligence, you're probably going to make $62,000 a year. But I would need to know what your IQ is, right? So if your IQ is 114, that would go in. Whatever your score is would go in for the X. And so this individual score on the X axis would go in right there. Then we have B. And this equation may look familiar. So think back, probably your sophomore, maybe your junior year of high school. You probably bumped into an equation that was y equals mx plus b. Don't ask me why we don't just use mx plus b. I'm not a history nut. I don't know why we didn't just do what everybody else did. For all I know, this equation came first and the mx plus b came later. But b here is actually what m was before. So b is our slope. And what we mean by that is the rise over the run. So hopefully this is starting to jog some of your memory on that. And when we think about it in terms of x and y, we can say that the rise is the change. We often represent change in statistics as delta. So it looks like a triangle, but change in y, and then run is change in x. And this gives us a sense from the b coefficient. What I can tell you is for every so many points increase in x, and let's say x is IQ, for every 2 point increase in x, what is the change in y? And so, or y prime really. So if b here, and I'm just going to make up a number, but let's say that b here was 3,000. What that would mean is for every 1 point increase in IQ, you would make 3,000 more dollars per year. And trust me, I don't know what the equation is, but it's not 3,000. It's probably something like $12 or something, if there's any relationship at all. But that's what that would represent is for every 1 unit change in X, for every 1 unit change, if X is IQ, for every 1 unit change in IQ, what is the change in salary? Now, to calculate this, what we can do is sum of squares xy and sum of squares x. So we're going to take sum of squares xy, we're going to divide it by sum of squares x, and the coefficient will give us the slope for our regression equation. So to calculate that, we need a few pieces of information. First, we need to know about the deviations of x. And so we go back to the mean of x, the average of x, and we say for this individual, for this data point, how much do they deviate from the mean of x? Now, I know up until now we've been kind of skipping steps. So when we first started, we did deviations, and then we slowly got to the point that we skipped deviations and just jumped straight to square deviations. However, now I need you to go back to just doing deviations, because eventually for this sum of squares x, y, what it is the deviation of x times the deviation of y. So it's going to be that product term. So you need the original deviations. So we're going to find the deviation of x. We also need to know the mean or the average on y, so we get y bar, and we find that deviation. And like I said, for this individual, their product term would be this deviation from x times their deviation on y. And for this individual, their deviation from x, so x minus x bar is greater than x, so it's going to be negative. Similarly, y bar is greater than their actual score. It's going to be negative. So again, going back to why does the correlation end up positive, most of the scores are in this quadrant or the top right quadrant in this data. So those product terms are going to end up being largely positive, and thus our slope is going to be positive, our correlation is going to be positive. So for sum of squares x, y, we have the sum, and we're going to have to do that, right? So the moment we see that sigma, the large sigma, we know we're summing this up for each individual. So I show you one, you would have to do it for everybody in the scatter plot. For sum of squares x, this is more similar to what you've done before. It's basically the square of the deviation of x. So we've seen x minus x bar before. It's basically that same thing. So you've already, to calculate sum of squares xy, you had to calculate the deviations for x. You might as well just at that point square those deviations. You have sum of squares x. And in fact, if you want sum of squares y, you would do basically the same thing. You would take the deviations for y and then square those. So you would have 5 columns because you would have deviations for x, deviations for y, the product term, so deviation x times deviation y. Then you would have square deviations x and square deviations y. And then of course you can sum those columns for sum of squares xy, sum of squares x, and sum of squares y. The last term is this a. And again, going back to your high school math class, A is the slope intercept. So by slope intercept, what we mean is that is the value, the predicted value of y, so y prime, when x is 0. So we need to extend this regression line, this fit line, until it crosses where x is 0, which happens at the y-axis. And so the question is, on the y-axis, what is that value at this point where x is equal to 0. Now, it's probably a nonsensical number. So if we're thinking about income, according to this, if x was 0, if IQ was 0, then the value on income would be negative. Well, that doesn't make any sense. IQ can't be negative. In fact, IQ on a standard test, I want to say can't go below 60. So it's not that that number makes any sense, but we still need it for the equation to work. The equation for that y-intercept, that slope intercept, is going to be y bar, so whatever your mean for y is, minus your slope, b, times your average on x, so x bar, and that'll give you a. And then once you have b and you have a, you can plug in any value of x that's useful to you that you would want, and then get y prime. So for example, if we know that x, the average IQ in the population, is 100, maybe we want to plug that value in and say, when you have an average IQ, what is the average predicted income for individuals? And so we could then get the value that way.